So now we will discuss about the unsupervised learning in the model 17. So unsupervised learning means a data set which doesn't contain any labels. That means we don't know what will be the output, or we don't know how to we cannot verify the classified data sets. That means we have to do some other approach to know that those data sets belongs to a particular class or not, or to predict it properly. So to do that, we use an algorithm called clustering algorithms. So clustering algorithms are some algorithms in which the input are basically the data set and some hyperparameters, which together works to get an output called cluster membership or clusters. So for example, if you see this, that let's say two features, age and BMI, and when we plot this in x and y axis, so we get the data sets something like this. So these data sets can be clustered like this, spherically. So these spherical shaped data sets are called clusters. Let's say C0, C1, C3. So these are the clusters, and these clusters are basically nothing but the classes 0, 1, 2, 3, 4, any number of classes. So these number of classes or these number of clusters are called cluster members or cluster membership. Any outlier, something like this, will be detected as a -1 cluster. The number will be minused, so like that. So there are only just two types of clustering algorithm. Basically, it's not types, it can be classified as two types of clustering algorithms. So first type is a type of algorithm in which it takes input as data sets, as well as it asks the users to put the number of clusters to be classified, and then it gives us the cluster and the clustered data set. The second type is it just takes the data set and it doesn't ask for a number of clusters, but we have to give some hyperparameters to classify or cluster it. Okay. So the first algorithm is called K-means algorithm. This is of a first type in which we have to specify the number of clusters. Okay. That number of clusters is called K, and means here is nothing but this algorithm returns the mean of those clusters. That means if it is classified, it gives us this particular mean of that particular cluster. So this algorithm provides the centroid or the mean location of the cluster. If two clusters are present, then the algorithm returns 2 points, C1 and C2. This tells us that there are classes, two classes with the mean points. So the process of finding the cluster is called expectation maximization algorithm. So what happens in this k-means is, first, as a user, we have to manually enter that, provide the information that there should be n number of clusters, or in this case, we just take two number of clusters are there in this particular data set. So when we specify this by the user, then the 2 points are randomly initialized in the algorithm. For example, this is the green color is the data set. When we give there are two clusters, then randomly 2 points will be initialized inside this data set. What happens is that once the points are there, these points will take the nearest neighbors to this particular point and nearest neighbor to this particular blue point. So whatever the data set which are nearest to that, it will be classified as cluster 1 and cluster 2, as you can see in this picture. After updating the neighbors of this particular point, this point will be updated. That means the mean point or the average point of this cluster will be updated. That means, as you can see here, it has the highest density. That means the mean point of this whole cluster will be somewhere here. As you can see, it is updated here. Same way the blue point will be updated here. So like this, after this again, the nearest data sets of this point will be updated, as you can see here, and the nearest point for this blue point. So like this, the process will go on, and till the point at which there is no point or just 1 point or 2 point which shares the same boundary. Until that point, this expectation maximization algorithm will run. With this, the clustering happens. As you can see, it is properly divided into two clusters. So this is how the classification of the dataset happens using clustering. So as I said, all the closest points to be initialized to the initialized mean will be classified as blue or red. Then the mean point is updated to the respective cluster. Okay, and again step C, it goes on. So if a point is in equal distance to the both the means or to the both the cluster mean point, then the process stops, and this point is given randomly to any of the clusters. Okay, so the overall goal is to minimize the intra distance, that means the distance within the cluster, that is I said distance within the cluster points. Okay, and the cluster point or the within cluster point. The intra distance is basically the distance between the mean and the cluster point. This means I would say this is the main point and this is the cluster point. So we have to minimize this point or within these points, within these cluster points. Okay, so that is the goal. So in this manner, there are two cases can happen. So let's say we have already classified the clusters. We have decided the clusters. Let's say C1 and C2. This is C1 and this is C2, which has three points, and C3 and C4, which has 4 points, and here 2 points. So which is the best clustering here? So how to do that? So let's say we have taken the mean point for this C3 C4 cluster. This is the mean point, this is the mean point. So the intra distance C1, for this C1 it will be D1 plus D2 plus D3 D4. So this is X, and C2 will be D5 plus D6, which is equal to Y. And same way for cluster C1 and C2. So the distance intra, this is cluster 1, cluster 2. The intra distance between the C1 is D1 plus D2 D3 is equal to 8, and C2 is D4 D5 D6 is equal to B. So if we add C x plus y and a plus b, which distance will be higher? As we know that the distance d4 here is added up, is higher in this, as it is added to this cluster, the distance will be higher respect to this c1 and c2, as we know that x plus y will be greater than a plus b, right? So meaning that the cluster which has less intra distance is the best. So in this case a plus b distance is less than x plus y. The cluster 1 c1 and c2 is better with less intra distance. So this is the best. Why? Because there is a condition which is called within distance versus the across distance. So in this case the within distance between this c1 and c2 is less with compared to the other one, so we choose this. But how? We will know. Why are we doing this? We will know this using the total pair distance case. So let's say like there are 6 points here, as we know. 6 points means how many pairs of distance are there? So that means 6 choose 2. That is 6 factorial by 4 factorial by 2 factorial is 15 combinations of that. The 15 combinations are written here like this. P1, P2, P3, P1, P3 like this. Okay. So these are total number of combinations between these 6 points. Okay. As you know here. So let's divide this intra and across distance. So the intra distance is nothing but the distance within a cluster. Let's say the distance within this point, this cluster, and within this cluster. So that will be P1 P2 P1 P3 P1 P4 and P2 P3 P2 P4 P3 P4. So this is one cluster, and this is the second cluster, P1 and P6. That means that total 7 combinations. And same for the across distance. So these are the 8 combinations. When we add both of these things, we get the total pair of distance, right? So from this we know a logic that the within distance plus across distance is equal to the total number of cases, which is constant. This will be always constant to the number of data set we have, right? So from this we can make an analogy that when the within distance decreases, the across distance will increase. So to have a good clustering, that means to properly classify the data set, it is necessary that we decrease the within distance. If it decreases the within distance, automatically the across distance will be maximized, right? So this relation basically properly classifies these clusters. Okay, so from this we understand that we have to reduce the within distance. So the clusters which has the low intra distance are properly clustered. So our goal is to minimize the intra distance. So mathematically it can be represented as the to minimize the distance between this between pi and pj for given cluster k1 to number of clusters, and this I is nothing but the number of points inside the cluster, and this j is also within the cluster. The condition is that the I is not equal to j as well as I is less than j. Okay, and I and j are both belongs to the kth cluster, and the distance we are calculating is nothing but the equivalent distance, which is nothing but the diagonal distance in the Pythagoras theorem. Okay, so this same equation is transformed to like this, in which we are using the mean value. Using this mean value, the calculation becomes simpler. That is why our computation inexpensive. That's why we are using this method. This this function is basically the loss function or the cost function, which we have to minimize. And here the value which we have to minimize is the mean value of the particular cluster, okay, for the given number of data sets, right? So if we minimize this, we will be able to classify the data set using the clustering algorithm. So one of the problem with this k-means is that, or the simpler version of this k-means is that we cannot determine the outliers in this. Okay, we can, if we advance this k-means, we will be able to find the outlier, but in the vanilla version or the simpler standard version, we cannot determine the outlier. So another problem with this k-means is that this method doesn't work for others other than spherical shape clusters. For example, if you have a shape of two half moon shape like this, shape or half moon shape, the mean of this point will be somewhere here, but it should not be. It should be somewhere here for the same thing. So in this case, the mean of these points does not represent the cluster. Okay, if it's outside it does not represent the cluster. So this mean should be within the area of this data set, but in this case it will be outside. So that's why this mean does not represent the cluster. So we have to use the median for this. The median means this is the point of the median. This is the point of this median. Median means it should be among the data set, right? And if you use the median, this method is called K-Medioid. This K-Method will be used for this kind of shapes of datasets. Okay, so K means goodness is calculated using the within and across distance. As we know, if the within distance reduces, the across distance increases. So how perfect, how accurate is this method has happened can be measured by within and across distance. The spherical shape clusters works good for this K means using the equivalent distance formula, right? So next we will talk about the initialization. So as we know, we have to randomly initialize n number of mean points inside the data set. So the best practice is to start or initialize the mean points as far away from the clusters or the data sets, right? So this is from the empirical evidence. If different means are allocated, then allocation of the clusters will also differ. For example, if you allocate two mean points, it means two clusters will be created. If you provide 10 points, it will be 10 clusters, right? It depends upon us how many clusters you want. So the final mean is susceptible or influences the initialization, right? So how many means you are providing will influence uh, the proper mean of the cluster. If you add too many initialization, there will be too many means. So we don't want that. We want an optimal number of mean to be initialized. So the best initialization is to let the n number of initialization find the minimum within our intra distance by minimizing the loss function. Okay, find one by one we have to give and compare, and the one which returns the minimum intra distance will be the best. So for what I was saying, that just put like initialize with one cluster, two cluster, three means one mean, two mean, three mean, just test it and calculate the intra distance between that. So as we know, if there, let's say if you initialize with one mean or one cluster, the intra distance will be higher. If you just go on putting many mean points, the intra distance will reduce. But the optimal K mean point, the K value is a point at which the difference in the intra distance is not significant. As you can see, the intra distance is significantly changing with the point to point. From this point to this point is not changing much, right? So that means this point is the optimal K value or the initialization value, or this point is also called a knee point or elbow point. Okay, so for clustering, to evaluate the goodness of the result, there are no ground rules. That means there are no proper rules to analyze that this is the proper to justify that this result is properly classified. Okay, the only way to find the goodness of this cluster is through the comparing the intra and across distance. So as we know that the vanilla version of the k mean doesn't have the outlier, what we can do is to find the outlier, we can modify the k mean algorithm that the outliers can be filtered by applying an intra distance condition. The condition is that the distance between the point, if the distance between the point pi and the is greater than c times the average inter distance. That means the average inter distance for this particular cluster, let's say it is di, 3 times or the C times this average distance. If this dp is greater than the C times the average intra distance, that means this point can be classified as an outlier. Okay, although this point may be or may not be inside the cluster. If it's even in the cluster, it will be uh, marked as the outlier. But anyway, we have to know that that point should someday belong to a particular cluster. So there are many algorithms in Python itself to determine the outliers. That list of algorithms are called PYOD, or Python Outlier Detection Library, which has more than 25 algorithms to detect the outliers. One of these for the k-means is k-mean-w, and for kn is knn-w for kn algorithms. Okay, so if they ask for a question that how can you identify the outliers, so there are some methods. Let's say z-score, interquartile method, clustering algorithm, like from the clustering, as we know, this k means w. In kn also we can identify the outlier using this kn w algorithm. Okay, right. So as we also discussed about the K-Mediods, which uses the median point in the cluster to create in the data set to create the clusters, right? So next we will talk about the evaluation matrix. So how to evaluate, how to value this accuracy of the particular cluster which we have created. So one of the famous unsupervised clustering metrics is silhouette score. It's basically a coefficient, so silhouette SS, we will refer to as SS. This measures the goodness of the clusters, right? So how do we identify the silhouette score? So silhouette score for a point, let's say pi, this is the pi. So the silhouette score for a point is the average distance across, the average across distance of pi with the closest cluster. So this pi belongs to the C1, and there is a closest cluster C2, and there is another one C3. So the closest cluster to this pi, which is in the C1 cluster, is C2, right? So the across distance for this pi will be d4, d3, d4, d5, right? So the average of this d3, d4, d5 minus the average of intra distance of the pi within the cluster, that means d2 plus d1 divided by 2. So that is what is happening. So divide by the max of a plus b. We will know what is a. The a is the representation of this average of across distance, and b is average of intra distance. So a is, as I said, d3, d4, d5 divided by 3, and b is d1 plus d2 divided by 2, and max of a and b will be here. So how can we know that similarity score is good? If this intra distance within the cluster is very less is compared to the across distance, at that point the SS score will be 1, which is the best. It means that it is the best, it is the best cluster. That pi point is in the best cluster. Okay, if the b is greater than, if the intra distance within the cluster is higher than the across distance, it will be -1. This means it is the worst case. The range of the similarity score is within -1 to 1. Okay, same way, doing the similarity score for the whole cluster is nothing but the summation of this similarity score for each point in that particular cluster divided by the number of points in that particular cluster. So this is the cluster for C1. So pi similarity score for pi, pj, pk divided by 3 is the similarity score for the cluster 1. How to find the optimal initialization value or k value for with respect to the similarity score? What we have to do is recursively for each mean point we calculate the similarity score. For the point in which the similarity score is the highest, will be chosen as the optimal initialization value or k value. Okay, there are other methods, other unsupervised evaluation metrics other than similarity score are Dunn Index or Davies Bouldin Index. Okay, so next we will talk about the supervised clustering metrics. So if it's already so, if in the data set there are labels, we don't have to use the clustering algorithm, because we have other methods like decision trees, k classifiers, other methods are there. But if we want to just create an accuracy and want to know the accuracy using this clustering algorithm, that time we have to use the labels for that particular data set. So if you have the labels for the particular data set, after performing this clustering algorithm, we will have the clusters. From the clusters, we can use a metrics called purity. Purity is nothing but if the clusters are happened like C1, C2, that means this is a class 0, class 1. We can just check the purity. Purity is nothing but the how many elements are perfectly classified. That means if there are 7 elements here, that means how many of this belongs to the class 0, that is 5 by 7 here, and for the class 1 it is 5 by 6. So we know the purity of this particular clustering here. And there's another method called random index, okay, which can be used. And another way of to uh, justify or find the accuracy of this clustering supervised clustering algorithm is to use, after having this clustered data, we can just pass on this classified clustered data set to the other nonlinear classifiers like addition tree or SVM or random forest or any other ADA boost or XG boost. We can pass through that and we can find out how perfectly it has classified. Okay. So next we will talk about the second type of clustering algorithm, in which we don't give any number of, we don't specify the number of clusters we need. So it is called a DBSCAN. It's nothing but a density-based spatial clustering of application with noise. So the output of this is it will give us the number of clusters and the classified data set, and also it will give us noisy points. Okay. So and one good thing about this algorithm is that it can determine the outliers. So, but one of the additionally, instead of giving the number of clusters, we have to give some hyperparameters. In this one is the EPS is nothing but the radius of the particular circle, and the other thing is the minimum point. So we will know what are these radius as well as the minimum point. So the idea behind this algorithm is that once we have the data set inside the algorithm, what happens is that randomly a point will be chosen in the data set, and it will create a circle around it, and the radius of the circle will be specified as from the EPS. And any point within this circle will create another circle. Okay, so likewise all the points within the data set will create a loop of circles like this. Many circles will start. So the region which has many circles, or uh, the region which has a minimum number of 5 points, that is min points, which has 5, it will be considered a cluster. Let's say if it creates a number of loops, many loops are there. If this loop contains uh, at least 5 points, which can be defined by us as 5, it has minimum 5 points, it will be judged or classified as a cluster, right? If a region has less number of loops or circles, and it has less number of points, less than 5 points, this will be considered as an outlier. Okay, so this process can be done basically parallelly or sequentially. So parallelly it will be much faster. Okay, so this way the DBSCAN returns the number of clusters. Okay, and one more observation is that this center point is called core point, uh, which this is called core point if it creates a circle, and within the circle it has more than 5 points. And one more thing is that these boundary points are basically the connection between the core points. Okay, so this core point, if there is another point here, so these are the boundary elements which connects or creates a loop between the core points. So DBSCAN was basically it's an extension of another algorithm called optics, and there is an advanced version of the DBSCAN, or the extension of the DBSCAN, which is called HDBSCAN, advanced versions. So again, another algorithm of type 1, which we have to specify the number of clusters, is called hierarchical clustering. So one of the advantage of this algorithm is that we can choose how many number of clusters we want. So what happens is that if you have a data set like this, and if you know the distance between the points, every point, so what happens is that it builds a dendrogram or this tree-like structure from bottom up as well as the up to bottom. So best will be to create a tree from bottom up. So what happens is that you will take a 2 points which has the least distance, which is P6, P5. It will take like this at level 2. It will create a cluster here. And again, the another second next least distance is P1, P2, which has 3 distance. It will go to level 3. So likewise, it will create a cluster from the subclusters like this. And in the final case, we will have the one cluster which has all the elements. Okay, so the idea is to develop a subclusters with least intra distance between the points, that is P6, P5 which has 1, and then P1, P2 which has 3. So just like that, join and build the subclusters in different levels. So this cluster is called Dendrogram, and this is built, most of them it is built from bottom up fashion, and this bottom of building of tree is called agglomerative algorithm. We will know about, we will implement this algorithm in our code section also. So in that, one of the advantages is that we can choose the n number of clusters. Let's say if we want to stop by just 3 clusters, let's say that will, we can just specify it here as 3. So 1, 2, 3, 3 clusters will be all the data set will be classified inside the 3 clusters. Okay. So likewise we can choose how many clusters we want. So one of the interview questions is that how to compute the distance between the points. So in this clustering, as we know that there are computation of the distance, there are different formulas like Euclid and Manhattan, Minkowski. So there are this way, but these are the formulas in which we compute distance between the 2 points. But how many ways we can compute the distance in the clustering algorithm? So there are 3-4 methods. One of the method is the single linkage. Single linkage is the distance between the closest point of the 2 clusters. Let's say these are the 2 closest point in the 2 different clusters. So this D1. So D1 is the single linkage. So this kind of distance are used. And if you use this kind of distance, the overall clustering shape will become a chain-like shape. Okay. And another way to calculate the distance is complete linkage, in which distance of the furthest point of the 2 clusters will be considered distance 2. In this case, it will give also elliptical shape which has a hollow inside. Okay. Another thing is average linkage, which is the distance between these. Let's say 5 points are here, 3, 4, 5, and here 4. That means 20 pairs of distance can be calculated. So the average is between these two points in the 2 clusters divided by the number of pairs, 20. Okay. So this distance can be also used, and this provides a shape of elliptical shape or spherical shape, and it doesn't have any column inside. And the other idea is centroid distance, which is the mean points between the 2 clusters, the distance between the clusters using the mean points. And another linkage is w.r.t linkage. Okay, so now we were discussing about one of the supervised learning algorithm, which is called Naïve based algorithm. It's a famously used when we have a large dimension of data sets, especially for classifying text data. So we will know about this Naïve based algorithm. So this algorithm is used for classification, especially for multi-classes. So as we know, the Bayes theorem, which is basically conditional probability, it says that if what is the probability of an event A given that event B has happened. So probability of A by B is equal to probability of B by A times probability of A divided by probability of B. So each element is called, this probability of A given B is called posterior, probability of A is called prior, probability of B is called evidence because it has already happened. Probability of B given that A is called likelihood. Okay, so we will know about this. We will use this probability to classify the dataset. So let's say a dataset is given like this: BMI, age, glucose, and Y is nothing but if the patient is healthy or it is diabetes. So BMI is high or medium, or age is less than 30 or between 31 to 40 or greater than 40, and glucose level is 120.1, something like that. So question is, what is the probability that the patient is diabetes given that the BMI is high and the age is less than or equal to 30? So this is we are just using the categorical features, not using the continuous variable real values. Just we are focusing on the categorical features. So what is the probability that the patient is diabetes given that the BMI and the age? So using this Bayes theorem, we can just say that the probability of what is the probability that the BMI is high and the age is less given that the patient is diabetes times the patient is diabetes probability of the patient to be diabetes divided by the probability that what is the probability that BMI is high and age is less than 30. So leave this likelihood, just concentrate on the prior, that what is the probability that a patient is diabetes, that is y is 1. So 1, 2, 3, 4. 4 by 7. The probability of a patient being diabetes is 4 by 7. And the probability that patient has a BMI high and age less than 30, that is basically 2 by 7. That is the evidence here. So how to know about the likelihood? We cannot just directly go to the likelihood because it doesn't exist here. Okay. A patient which has BMI high as well as age is low is here, one is there, but we need to know that how do, because these features are dependent, not independent. So what happens is that with the increase of age, the BMI also increases, the glucose level can vary, and that means this age as well as the BMI are dependent, right? So dependent variable cannot be just predicted like this. Okay, so the likelihood are dependent features, so it need to be separated to find the probability. So one of the assumption of the Naïve's Bayes theorem is that, so it is, this assumption is that all the features in the data set are independent or mutually exclusive. That means both the events cannot happen at the same time. So this is a Naive assumption. That is why it's called Naive Bayes assumption, right? So as you assume that BMI as well as age are independent features, so this probability can be taken as probability of the BMI is high given that y is 1 times the age is less than 30 given that y is 1. So if we divide this probability into 2 like this, so we get the probability 3 by 4 times 1 by 4. So if you use this value here as likelihood, we will get the probability as 3 by 8. Okay. So once you know the probability that, what's the probability that given this sample BMI is high as well as age is less than 30, what is the probability that the patient is diabetes is 3 by 8. So if we, what is the probability that given this sample is not a diabetes, it will be -1, right? So this is the probability, this is the probability x here. If it is not a diabetes or healthy person, just we have to use -1 minus x, right? And the threshold is nothing but 0.5. So if the x is like let us say 0.6, if x is 0.6, that means it is definitely a diabetes patient. That means there is a 60% chance that it is a diabetes patient for the dual sample. If it is 0.4 for this, it will be, there is a 40% chance that it is a healthy person. So this was used for the binary classification, binary class, the 0, 0 and 1. So if you want to use for multi classes, what you have to do is just put the sample here, the same BMI is high and the age is less than 30, and what is the probability that it belongs to the class 1, class 2, class 2, class 3, like this. So whichever probability is high, let's say for 3 it is 0.8, that means the particular sample belongs to the class C, class 3. Okay, so this is how we do it for multiple classes. So till now we just dealt with the categorical features. So now we will know how to find the probability for using the continuous features also. Let's say glucose here. So under assumption, when we are involving the continuous feature, is that we find the probability assuming the Gaussian normal distribution. Okay, assuming that the particular data set is normally distributed, that it has a bell-shaped curve. Okay, if we have assuming that it is a normal distributed, if it is normal distributed, then we can find the probability of a particular event happening from the formula. It is called probability density function, which is this. Okay, and this mu is nothing but the mean, and sigma is nothing but the standard deviation of that particular class, of the particular sample. Okay, if you say the particular samples, say what is the probability that is a diabetes patient. So diabetes patient means only those values, only those samples, so say 1 1 1, whichever about 1, those, only those glucose samples will be taken, and the mean of that sample will be used here, or standard deviation will be used here. Okay, so in this case, uh, if it is asked what is the probability that glucose is 140.2, which doesn't exist in the data set, what is the probability that glucose value is this, given that it is a diabetic patient? If the data doesn't exist, it doesn't mean that probability is 0. what we do is we create a very small value for that. Uh, it's called Laplace smoothing. We'll know about that. So we'll know why. So when we use this assumption, Gaussian assumption or non-distribution, this algorithm, this theorem is called Gaussian namespace theorem. So what is the probability that the patient is diabetes given that the BMI is high, glucose is 140.2? So we use the Bayes theorem here. This is the likelihood, prior, and the evidence here. So basically, we don't need to calculate the evidence because the probability depends upon the numerator value, right? So we don't have to compute it. Just for the to reduce the computational expense, we are not in the algorithm. We don't basically compute the denominator. So we only use the numerator. So the likelihood, as we know, we have to take this. We have to consider it as an independent event. So the probability of what is the probability that BMI is high and the given patient is 1 times the glucose is 140 given that Y is 1. So if we do that, as you know, as we discussed, this data doesn't exist, doesn't mean that it's 0. So we just take the very small values and consider it like that. And then we compute the likelihood. Okay, and then we finally get for a given sample which also has a categorical as well as the continuous value, we can find the probability. Okay, so there are some observations. So Naïve algorithms works best for the text dataset. It works good for dataset with large dimensions. If the evidence is like this one, technically it is 0. So, but the posterior probability will become infinity. Let's say, yeah, this condition is very small. This is very small value 0. Let's say if we put 0, then the whole value like any numerator divided by 0 will be infinity. So we don't want an infinity value. So that's why we are putting a very small value 0, 0 0.0, something like that, so that the probability will get reduced and there won't be any mathematical error. And this adjustment of the given probability to very small value or using the epsilon value is called Laplace smoothing. Okay, so then we will discuss about the market basket analysis, which is basically a recommendation system to uh, recommend a particular product or suggest a particular data to given to new customers or to the retail shoppers. Okay, so what happens is that we have a data set which has, let's say, a normal product user relations. So we have data that a particular user bought this product, this quantity, or this can be a one-hot encoding like that. Let's say a user bought this product, it will be classified as 1, and if it's not bought, it will be 0. It can be like that. It can be a product matrix with the quantity or units. Let's say a user bought 4.5 kg of something. So this can be any format. This is called user product matrix. So if there is a new user, so how do you recommend or generate recommendation for the particular new user who is browsing a particular product? Let's say, yeah. So the idea is a content-based approach. So a content-based approach is nothing but, let's say, a user K is browsing PK product. So what we can do is we can show or recommend a rated product with respect to the category. Let's say uh, he's browsing a movie CD. So what we can do is we can recommend all those movies which are directed by those director which he's browsing, or the actor which is the who played a role in that particular movie. So we can use the characteristics of that particular product, and I can show or recommend the product for that user, right? Or we can just uh, a series which has a similar price range, we can also be recommended. Okay, this method doesn't use any of the information from the product matrix, but it uses all other resources like from cookies, what is the history behind the users. So it uses everything uh, other than the product matrix. So it's one of the popular method to use to just know about the user, what he needs, what he doesn't need, and generalize, create a recommendation for that. It's called content based. So only searching or recommending with data of UK is called content based. Other one is the product similarity. So product similarity is nothing but, let's say, the new user is browsing a product PK. If this product is bought by some other users, and we have to analyze that other users what else he bought with those products. Let's say the other user bought PK, PIPJ, so we can just recommend PIPJ, PM. We can recommend this product to the new user. So this can also happen, right? So what happens is that from the product matrix, we can just take the similarity. Let's say he's browsing product P1. We can just find out the similar products of P1, so PY like from the column wise. We can just find out the relations or create a correlation data set so that we can recommend it. So it's a column based perspective, and this is called basically frequent item problems or a priori. And another one is the um, user similarity. So what happens is that we use a distance metrics to find the similar users. If the user K is there, you will find distance metrics to find a similar user with respect to the age, gender, or type of race, something like that. We use distance metrics, for example, correlation, Euclidean distance, Manhattan distance, square distance, dot product, cosine similarity, divergence vectors or probability, etc. So it's a row-wise perspective. So if there's a user key, we will find the similar users, and for the similar user, what are those products they found. So if the common products are, let's say, P3, P4, so we will recommend that. If there are other products like P1, 3, 5, 7, if they are bought once, so what we can do is that we will just know that which product sold overall best. We will recommend that. Okay, so these are row-wise perspectives. So taking like this. So another method is the fourth method is collaborative filtering, which is basically a mathematical approach. Uh, so what happens is that the product matrix which you use is basically a highly sparse matrix. That means it has too many zeros. Okay, so most of the vectors are zero, and it creates a computational expenses. It increases. So if the dimensions are high, the similarity between the columns or the rows will be difficult to compute. So the distance matrix won't give any intuitive insight from the product matrix. So this kind of situation is called curse of dimensionality. It means if the number of dimensions is too large, the distance between the two data points doesn't make any sense. Okay. So the remedy is to reduce the dimension of the matrix. It's called dimensional reduction and can be done linearly and as well as non-linearly. So to reduce the dimensionality, we have to use a method called SVD, which is called singular value decomposition. So let's say we have a product matrix which has a dimension n times t, and t is the number of products or features, and n is the number of users. And we have to reduce to n times m. M is the new features, which is very less than the d. Okay, and this is called uh, latent features. The new features are called latent features. So let's say somehow we are able to convert these m features. We are able to find features with the linear as well as non-linear relation. Let's say alpha 1 times x1 plus alpha 2 times x2, like this. This is a linear relation. If we just make a linear relation, we can create the first feature. So likewise, we can also add a x square, x cube, like this. It becomes a non-linear relations. So likewise, we can create a linear relation, and we can create m number of new features with this kind of relations, and just we have to know about these alphas. Okay, so these new features are called latent features, which are defined linearly with the original features. Doing so, the sparsity of this original product matrix is reduced, and it densed in these new features. So how do we do this basically? How do we create these relations? So this kind of relation is basically done through this matrix form. Let's say this SVD, this singular value decomposition, what happens is that it reduces this or decomposes this matrix to three matrices like this: K n times n times t times t. So this is called U, epsilon, and Vt, V transpose, and this is called U. So what happens is this particular matrix, this epsilon matrix, is called block diagonal matrix. It's nothing but a diagonal matrix which has elements only in the diagonal, and other parts are all zeros. And these diagonal values are called eigenvalues, and this values put in a vector is called eigenvectors Okay, so what happens is that we will just sort this eigenvalues descending order. This eigenvalues, let's say sigma lambda 3. Lambda 3 means the lambda 3 means third feature D3 or X3 is important, is the most important feature in the whole product matrix. So this will be taken. So what happens is that we have to choose, as we have to choose the number of latent features. Let's m is 20. That means we want top 20 important features. So what happens that after putting these lambdas in the descending order, we have to just take the top 20 lambda values. Top 20 lambda value means top 20 features are selected. Okay. So once we have set that, it defines the importance of the particular features. So what we do is in the U matrix, we will take all take out all the columns which are not in the lambda. Let's say here lambda 10 is not there. Lambda 10 is not in the top 20. That means you will take out the 10th column. You will take out the 10th column, and all those columns will be taken out. Only n times 20 matrix will be here. So we are reducing the U matrix. Same wise we will reduce the V transpose, in which we will remove all those rows which are not in the lambda, which are not in the eigenvector. This will become 20 times D. So once we have n times 20 and D times 20, the overall matrix will be smaller. Okay, it will become n times 20 itself. So we will use this n times 20 when the users, we want the users in terms of the features. These are defined users in terms of the features. D times 20, that is the V transpose, are basically products in terms of features. So for similarity between the users, we will use this matrix. For similarity between the products, we will use this matrix. Okay. So SVD, a single value decomposition, can be used from NumPy library, numpy.linearalgebra.svd. It will give the three matrices. We'll see that in the coding part. And the other method is the model based recommendation. What happens is that if we just use the classifier many model, just train the model with the above data set and then put the test data set, it will just tell us which part to does we have to recommend this part or not. Okay, so this can be done. So that's all. Now we will discuss about the coding part. So in the coding part, we will know, we'll talk about the clustering. So we'll talk about the k-means, seniority score, DBSCAN, and agglomerative clustering. So first we have to make a classification dataset which has 100 samples and 5 features, and just we put it in the pandas. You can see it here. Let's plot the scatter plot here. So this is scattered like this. We will use k-means method to classify this. So we don't have any y labels, we don't have any labels. So we are going to use k-means, which has this index like this, n number of clusters which you have to specify, and how many initialization you are going to put, which method k-means plus number of initialization. 10 initialization are basically used. 10 times the initialization will happen. Okay, that means 1 2 3 4 like this, it will create 10 times the initialization, and maximum iteration is 300. Okay, so once we put the number of clusters, we want two clusters, 0 and 1. So then we fit the model here, just two rows, 0 and 1, and that's two rows. When we put the model, and if we just take the labels here for the 20, for the two columns, this is the answer. So this is basically the binary way of doing it. So if you just plot this data set from the model labels here, so data x1 x2 is q1. So same way, here also only two variables x1 and x2 are q1. So for this you can see that the labels are like something. So this is how it's classified. So let's find how good this is classified. So the what we're going to do is import this Reuters code from the sklearn.metrics. So just we have to put the data set, the two labels, the data sets, as well as the output label. So it just shows that it is 54% accurate. Okay, to find the best sliders, to find the best sliders as well as the k-mean. So what we have to do is to create a recursive approach for k is the number of clusters from 2 to 20, and for each one we will find the Solaris score. So if you do that, we just know that our best Solaris score is 15%, and it is for the k is equal to. Okay, so this is how we know that. So let's say we normalize this data set. The data set is given, so we just normalize it, and we fit the normalized data set into it. So we will see what happens. So we just get the labels. So what happens is that we uh, when we normalize this data set, what happens is that we are getting too many clusters, 7 clusters I think totally. So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 clusters of them. Okay. So these are the cluster locations. Cluster centers is nothing but x comma y. So for 8 clusters, 8 coordinates. So if you want to predict for a particular value, so let's say this is a particular value. So what is the, so which class does it belong to? It belongs to class 1. So this value can be identified right here from here like this, 0.82 comma 0.41. So it belongs to class 1, not class 0, class 1. So we can just know that. So let's go to the type 2 of the clustering, that is DBSCAN. You can just import it from the echelon.clusters import cluster DBSCAN. So just you have to insert the radius as well as the minimum samples to be inside the circle. So we fit the trained dataset or normalized dataset with the first 2 columns. Then we classify the labels. So as you can see, the minus means these are the outliers. So if we just plot it, you can know that there are different clusters from the DBSCAN. Okay. So from this we know that these are the number of clusters and how many elements or how many data sets are there in each cluster. Here it means there are 6 outliers. So next approach is the agglomerative approach, which is basically a hierarchical uh, approach, hierarchical clustering. So what we have to do is, in this case, we have to give a number of clusters, how many clusters we need, and linkage type for the agglomerative approach, how the distance has to be computed. So in this case, we are using single. We can also use complete average or centroid, as we know. So yes, again we are we are fitting this trained or normalized data set, first 2 columns. So in this case, as we have specified the number of clusters, it is giving only the number of clusters here. In the K-means also we specified the number of clusters, right? In this case, we just specifying it, and we just know the difference. As we know that the K-means was quite different from this, and here it is quite different. Okay. So from the Solaris score, it is 50%. That means it is not performing as much as K-means here. Okay. So now we will discuss about the other file. It is market basket analysis, which we just discussed. So in this case we are using the load breast cancer dataset. So there are 569 dataset samples and 30 features, which also includes the target. So we are just feeding these values in the pandas. So these are the described functions. 70% mean value here is given. Okay. So now the target value, as you know the names, so misalign and begin is nothing but the 1 and 0. Okay. So the output, which is classified, so there are 357 ones and other zeros. So what we do is split train and test data set. Then we standardize it using the standard scalar from the pre-processing from scalar. We just fit the xtrain and transform the xtrain as well as xtest. Then again we normalize it. Normalize using the mean value. So that is nothing but xtrain minus xtrain dot mean. Same way for xtest minus xtest dot mean. We use this normalized xtrain and xtest in the single variable decomposition, that is SVD. We find the covariance. Covariance is nothing but column times columns. So it is a basically symmetric column. As we know, the shape is 30 by 30. is nothing but A matrix. As we discussed earlier, A is equal to U times epsilon times V transpose. So here it is that A matrix here. Okay, so this is the A matrix. So this SVD will decompose into three matrices as we discussed earlier, right? So what we do is we factorize this covariance A using this NumPy library SVD. So what we do is import this SVD from NumPy.linear algebra. We just import this covariance A matrix, and this will give us U, S, and VH. What is the shape of this? U is 30 by 30, 30, and VH is 30 by 30. Okay, because it is a square matrix, so that's why it is giving like this. So the eigenvalues, that is the block diagonal matrix in descending order, is the third 30 values. It is here. So it is in the descending order already. So if we want the values to be between 0 to 1, so we want this value to be between 0 to 1, so what we have to do is, if you put this value between this eigenvalue between 0 to 1 value, one range, it is called explained variance ratio. So it is basically the value divided by the sum of this value. So in this case we will get 0 0.97, 0 0.98. This means that this particular feature is 97% important, or it covers 90% of the variance. That means it covers the variance or the spread of the data set. It is the particular feature is 97%. Okay, this is that much important. So now we want uh, to decide how many eigenvectors uh, we need to select for the final dimensional reduction. So we need to find, like in the theory we just mentioned, like top 20 we need lateral features. So we need to have some threshold feature. The threshold is 98%. That means that particular feature should cover the 99% of the data set. So that is the threshold here. So for that we have to simply add up the explained variance ratio for the particular eigenvalue. If the addition of those values, eigenvectors appear to the 98%, that means the threshold is met. That means from this method we just know that top eigenvector has 91% of variance. If you add that eigenvector 2 also, it becomes 99.7%. It means 19, these two eigenvectors covers the 99.7% of the data set. Okay, that means our number of eigenvectors is only 2. The two latent features are selected already. So then now we are going to reduce the dimensionality. So by just simply multiplying the U times it's a matrix multiplication, that is the extreme times the transpose of U. So this 2 is nothing but the eigenvectors to be selected, right? So this is what happens. It just takes the top two columns, 0 and 1, takes the top two columns. Because it's already, this is already sorted out. It is in a descending order, so only the top two features will be there in the multiplication. So this extreme matrix will be multiplied with this U transpose. So once we do that, the projected train will be out. This is the proper projected matrix data set, which is a reduced data set. So when we plot this, the projected training data, all the rows with the first column and all the rows with the second column, using the variation from the y train dot values as it's already classified. So when we do that, we can get this kind of projection. Okay, as we know, obviously we already have the uh, it's basically a supervised data sets, as we have this. So same thing we can do for the test data set. We just multiply this normalized x test times the Q matrix. So same way we just do it, we get this kind of classification. Okay, which is basically from u1, vector 1 and eigenvector 2. It is classified. So next, this what we did using SVD, we have to compare it with the original as well as the SVD dataset. So what we do is we just know how this dataset are performing in the given classification algorithm. So in this case, let's say your logistic regression is used. So you're just fitting the normalized trained data set, which we got it from normalizing the original data train set, and we are using the accuracy. So accuracy of the training data set test is it is here 95% and 95.3%, 95.9, 95.9, so 95.32. Okay, so now we are going to use the projected train set from the SVD after reducing the uh, data set which had almost 500 samples and 30 attributes. In this case, the projected train will have 100 samples and 2 attributes. If we just calculate the accuracy, it's quite low compared to the other one. So this happens, but this SVD is basically for those which has high dimensions, very high dimensions. Sorry. So in this case, the logistic regression for the user data set works fine, works good, better than this. So the same SVD can be used from a package called Principal Component Analysis (PCA), which is from sklearn decomposition. So this is a linear dimensionality reducer. It doesn't use the nonlinear x-bar like that. It doesn't use. So in this case, we have to specify how many eigenvectors should cover the 19% of the variance. So in this case, we give 2, and this we have to train the normalized train data set. It will give us the eigenvalues or variance and the eigenvectors also. As we know, that it will be similar what we found through in NumPy. It is same eigenvalue. In the previous case, we got 30 eigenvalues, right? So, and the top 2 were also selected. So these are the top 2 selected eigenvalues. And the variance, as we know from the previous case also, the top 2 features which have the variance 97 and 1.8, it is same. And this is the eigenvectors for all those data set latent features. So these are the 1, 2, 3, 4, 5, 6, 7 times 4, 28, 29, 30. So for 30 features, these are the 30 uh, values. Okay. So next is the we can use this as we discussed. We found manually the U matrix. So in this case, what we do is just compute this U value from just PCA.components and just multiply it with the X train value. You will get the projected train value. So we just plot this projected train value here. We will get the classified samples. Yeah, like this. So again, the transformed A. So we can actually can get the transform data from the transformation function. So PCA.transform will give us the transform data. This is the, as you know, 300 data set and only 2 features. In the previous case, we just did it manually, right? So this uses the direct results. So and another method is called kernel PCA, which is basically a non-linear dimensional reducer. So what happens is that we just have to fit the training model and then transform the training model here. Transform training model will just directly give us this data set. So once we project the data set, we can just get the graph how it is projecting for the training data set and test data set. And what is accuracy, training accuracy and test accuracy. So it's 72%, 77%. Okay, so it is basically test accuracy is higher, that means it is underfitting. So another method is TSNE. It is a T-distributed stochastic neighboring embedding. So it is basically a similar method, but it is the problem with this is the cost function is non-convex. So it is recommended that we use other methods. So what we do is just provide the how many classes you want, then how many classification you want, and then provide fit and transform the training dataset, normalized training dataset, and just transform the dataset. For first column and the second column, we just we classify. Oh, yeah, classified, or should we 0 or 1, the particular sample belongs to 0 or 1, we can just know from this. So that's all for this module. Okay.